Hello everyone, I'm Sarah, and today I'm going to be doing a little video lesson on the AP Calculus BC FRQ from 2008 and question number 6. This video is going to be super helpful if you're prepping for the AP exam in May or if you're just reviewing for your final. This one isn't too gnarly, so hopefully I can help you out with it. Let's get started. So first of all, I wrote down some cool things to remember about this particular FRQ. First of all, number 6 on the FRQs for Calc BC generally involve a Maclaurin or Taylor or some sort of series. So that's actually why I chose to do number 6, because I was like, oh, I need help with it. Anyway, next, FRQs on the AP exam are generally pretty consistent in their patterns. So like, there's generally always going to be one tabular data problem or one series problem. So it's good to practice with a good variety of them. And next, the AP Calc BC exam is cumulative, so make sure you're studying your stuff about from Calc AB, because when I took the exam in May, there was definitely a lot of AB stuff on there. And finally, number 6 is on the non-calculator section, so make sure you're putting your calculator away for when you're practicing with this problem. So here is the FRQ in all of its glory. It looks really, really complicated, but this one is awesome because it combines a little bit of logistic growth with series and Euler's method, and it's just a good all-around practice for the exam. So question A gives us a slope field, and all we really have to do, so part A is really easy, all we have to do is just sketch the solution for the points 3, 2, and 0, 8. So as you can see here, I made sure to highlight those points, which they already pointed out on the graph, so that's awesome. And then you just kind of trace a line through them. Make sure that you're following the general slopes, because how a slope field works is it just shows you the derivative, what it's like at certain points. So make sure you're kind of generally following the shape of the slope field and not actually touching the line y equals 6, because that's the horizontal asymptote. Alrighty, for part B, it asks us to use Euler's method, starting at t equals 0 with two steps of equal size approximating f of 1. So I do Euler's in a slightly different way than how they show you on the actual FRQ key. However, it definitely works, and when I did this problem as practice, I got the right answer. So I'm just going to show you my way, but you can definitely check for the key online. So basically what we're doing for Euler's is we're using the derivative function to kind of approximate generally a certain point on the graph. So first of all, we're going to start off with the point 0, 8, and we know that dy dt at y equals 8 is negative 2. We plugged in 8 to the original dy dt function, and we got negative 2. Then you set up a point slope equation. So you do y minus y1 equals m times x minus x1, and I plugged that in and I got y minus 8 equals negative 2x. And then since they asked us to do two steps of equal size, you know that your steps are going to be 0.5 because 1 divided by 2 is 0.5. So I plugged in x equals 0.5 because that's what 0 plus 0.5 equals. And I ended up getting y equals 7. So that's our second point that we're going to use, 0.5, 7. Now we're going to use that point and plug it into the derivative function so we get what would be the slope at that point. This is really important. So we get what would be the slope at that point. We plug in y equals 7 to the dy dt equation, and we get negative 7 over 8. Now we plug this back into a completely new point slope function. So we still do the same thing, y minus y1 equals m times x minus x1, except this time m equals negative 7/8, x equals 0.5, and y equals 7. For our final step, we're going to plug in x equals 1 because that would be the second step of equal size. So you get x equals 1. And you plug that into the equation that you just made, and you get that y equals 105 over 16. So very roughly, according to Euler's method, f of 1 equals 105 over 16. Now for part C is a little bit gnarly, but not too bad. You know, we're Calc BC students, we can do this. it asks us to write the second degree Taylor polynomial for f about t equals 0 and use it to approximate f of 1. Make sure, this is a really common mistake, make sure that you're not just getting the second term of the Taylor polynomial. That's a really common mistake that students make. So the general structure that we're going to follow for Taylor polynomials is the nth derivative of f of a over n factorial times x minus a to the n. And I wrote that out for you so you can see it. And in this case, our a is going to be 0 because they said it's going to be about t equals 0. And n will start at 0 and we're going to work our way up until we get x to the 2, or something x to the 2. So that would be our second degree Taylor polynomial. So first of all, we're going to start with n equals 0, our first term, but we're kind of at a roadblock at first. F of 0 of t would just be the original function, but we're not given the original function here. However, we're given the solution f of 0 equals 8, so if you plug in 0 to the original equation, you're going to get 8. So therefore, we don't really have to find it. We already know that it's going to equal 8 at 0. So that makes our job easy. The 0th derivative of f of 0 over 0 factorial times x minus 0 to the 0, anything to the 0 power is 1. So we just get that our first term is 8. Awesome, easy peasy. For our next term, we have n equals 1. So that's going to be the first derivative of f of t, which is just dy dt, which is given to us. So sweet, we just have to plug and chug, plug in t equals 0 to there, and we get that the derivative is equal to -2. Therefore, the second term of the Taylor polynomial, sorry about that. The first derivative of f at 0 over 1 factorial times x minus 0 to the 1 is just going to be -2x. So awesome. Next we have n equals 2, so that's our third term. And for this one we're going to have to find the second derivative of f at 0. So basically what we're going to have to do is we're going to have to take the derivative of the derivative equation that they gave us. And that we're going to get d squared y over dt squared. So in doing this, pretty simple, we just take the derivative, and you can see I did all that work for you. However, since we're taking the derivative with respect to t, we have to multiply by dy over dt. And I think you might remember this from maybe pre-calc when you did like the derivatives of circles or something. And so we're going to follow that process out, make sure that you multiply by dy dt, which is just the equation that they gave us, and plug and chug y equals 8, and you get that the slope equals 5/2. So f double prime of 0 over 2 factorial times x minus 0 to the 2 is just going to be 5 over 4x squared. Awesome, so we got x to the 2, and therefore that's our second degree term, so there we go, we're all done. So our Taylor polynomial for the second degree is just going to end up being 8 minus 2x plus 5/4 x squared. And then to approximate f of 1, we just plug in x equals 1. So that's pretty simple, and we end up getting 29 over 4, which is a really weird number, but it's correct. Finally, what is the range of f for t is greater than 0? This is not the carrying capacity. That's what I thought when I first did this problem. But basically what we're going to do is they give us an original solution to the equation where f of 0 equals 8. So we're just going to get that function. And if we graph it, which I did, based on the slope field that they gave us, we can see that it starts at 8 and it only decreases. So if we're only looking at from t equals 0 to infinity, the slope is constantly negative, and it's always going to stay negative from 0 to infinity. So therefore, we know that the range is going to be from 6 to 8. You can see the function is going to start at 8, and then it's only going to decrease, but it's never fully going to touch 6. Alright, so that wraps it up. Thank you so much for watching, and I have some helpful links in the description as well as the original